This is section 3.5 of Timberlake Basic Chemistry on specific heat. Now, it's possible that this is the first section in the book that you have no previous knowledge about, that you don't know what this even means. But we've looked at it a minute before. We looked at the fact that 1 calorie was the amount of heat required to raise 1 gram of water 1 degree Celsius. Well, that is the specific heat of water. It's how much heat that water holds on to. So every substance in the universe is going to hold on to heat in a different way. Imagine on a hot summer day, the grass is receiving the same amount of heat from the sun as the sidewalk is. But if you're in your bare feet, I would rather walk on the grass than walk on the sidewalk, because the sidewalk is too hot for my feet, and the grass has cooled off more. Even though it's in the same environment, it should be receiving the same amount of solar energy as the sidewalk, but it's releasing its heat easier, and so it doesn't burn my feet. If you think of a frying pan, I can put a frying pan on a fire, heat up that frying pan very, very fast, but also if I were to turn the fire off, that frying pan would cool off very fast. Water, for instance, if you were to have spaghetti water, takes forever to get hot, but once it's hot, it holds on to that heat for a long time. So every material is holding on to heat. That's called its specific heat, or its specific heat capacity, and that's what we're looking at today. So when we said that 1 calorie was the amount of heat it took for 1 gram of water to go up a degree Celsius, that's the specific heat of water, which is either 1 calorie or 4.184 joules. Every substance has a number that you could assign to. So the definition is 1 gram of that substance raised by a degree, and it's going to be in joules per gram. And it could also, the metric system is in calories per gram, so it depends on what you're being asked to do. And then that is going to be every substance, every material. Water is one. Everything else has its own. So rubbing alcohol from the medicine cabinet is not going to have 1 calorie per gram. It's going to have a different amount. Okay, so it's actually more, 2.46 joules per gram rather than 4.184. So that's like half as much heat capacity in alcohol as in water, but yet it looks the same when you look at it. So if the heat equation, what you're going to actually use is going to be, you have grams times its Celsius, and if you want to find joules, you're going to have to use some kind of an exchange from how many joules per gram, and that, remember, 4.184 joules per gram in water, and then to find joules. Okay, so how much heat is gained by a substance as it changes, or how much heat is lost by a substance? You're going to have to figure the change in the temperature, the amount of stuff you have, and the specific heat of the substance. So for instance, let's say that I have something that's hot. Let's say I have a piece of metal or a piece of glass that I've melted, so it's red hot glass, and I put it in some water. Immediately the water temperature is going to go up and the glass temperature is going to go down, because the heat is going to go from the high hot glass into that water. Well, glass holds on to heat differently than water, so you're going to need several things. You're going to need to know how much glass you have, what's the grams of that, how much water you have, how many grams of that, the specific heat of the glass, the specific heat of the water, and how much temperature went up. So how much did the temperature of the glass go down, and how much did the temperature of the water go up? So the heat transfer, we can find out how much energy is transferred as we fiddle and find out about the materials that heat changes from. So we figure out what we're given. We calculate how much the change in temperature was, and then we're going to use the heat equation, and then substitute and solve for whatever we're looking for. So let's look at an example. The layer of copper on a pan has a mass of 135 grams. So that's the amount of copper. How much heat in kilojoules will raise the temperature of the copper from 26 Celsius to 328 Celsius if the specific heat of the copper is 0.38 joules per Celsius for a gram of Celsius? So we have the amount of copper on the bottom of the pan. We know how much that is. We know that we want to raise it from 26 Celsius to 328 Celsius, so that's the change in temperature. And we know its specific heat. So we can put it in the formula that we were given a second ago and simply solve for our unknown. Okay, so we first of all need to know what's the change in temperature. So we take 328 minus the 26. So we find out that it's changed 302 degrees Celsius. And then our heat equation is grams times the change in temperature times the specific heat of copper. So we're just going to multiply that out, and that's the heat in joules that's required to do it. So we have 135 grams times the change in temperature, 302 Celsius, times the specific heat, 0.385. And now that's going to give us joules, and now we have to divide by 1,000 to turn it into kilojoules, and we have our answer. Here's another example. What's the mass of aluminum if 325 kilojoules of heat raises its temperature from 20 to 45, and they give you the specific heat of aluminum? So you're going to put the 3 in the formula and solve for the other. Okay, so in this case, you're given the specific heat, you're given the amount of energy, and they want to know grams. They want to know your unknown. So really, it's a very simple Algebra 1 question. They're going to give you everything except 1, and then you solve for whatever you don't know. So as it's substituted, you're going to put everything in and then solve for grams in this case. So you have to get everything on the other side, grams on one side, and you can solve for it. So knowing that heat always transfers from the hotter object to a colder object, that energy can do things. It can make things move. You put energy into a balloon and release that balloon, the balloon's going to go all over the room. It's that kinetic energy is going to come from the potential stored. So that heat that you put into it can make things happen, or the energy that you put into it can make things happen. A lot of times it's going to be some kind of a molecular motion. So it's going to get hotter or colder. All right, just like you rub your hands together, you put kinetic energy into your hands to move them, and you warm your hands by friction because that heat and that stored energy is related. To do it in the lab, we're going to use a calorimeter. And a calorimeter is really just a thermos bottle, and that thermos bottle is going to have some kind of water, usually, and then some kind of an object. And the hot object, you're going to be able to go from that hot object into the water and change its temperature. So we'll play with this in class, and hopefully this will start making some sense to you.